Questions from the homework? Yep, Gabe.
Can you explain number 10?
Number 10. Oh, yeah, that's the last question. I don't really want to talk about it. I mean, like, I can explain it, but as I said, this pertains to that material that I said the AP exam will ask you precisely one question about it. Maybe. Maybe. Some years they don't even ask any questions about it. I can't explain it. It's something I'd rather do in office hours, which I have today after school. It's just too long to really be worth it. Yeah. What else? Anything? Yep, that.
I'm thinking the
Classwork number 2.
I had a question about
What the units were and what they meant.
was like the past 6.
So the function, so okay, essentially this is your variable here. We can call that x, and that's your function f of x. And so your variable is measured in hours, and then your function is measured in cars per hour, right? So the integral of this function, which of course you can only approximate, from 0 to, what do we want to do? I guess 0 to 2.75 is what they're looking for here. This integral would be measured in units of what? It would be the units of the variable. So this thing is measured in what? So units of the variable would be hours times the units of the function, which is measured in cars per hour. And the hours cancel, leaving you with just cars. Is that okay?
Yeah.
So whatever this integral is doing, it's measuring cars. So whatever quantity it's measuring has something to do with cars. What it actually is, in this case, is just the number of cars that went through the intersection over that interval of time. That's all it is. So it's the number of cars that went through the intersection from, I guess, 6 o'clock to 8:45. That's what those hours would correspond to. Is that okay?
Yeah.
Sweet. What else? Yep. Oh yeah, it's definitely an estimate. Estimating an estimate. Oh yeah, there's this weird bit about the computer predicting. That doesn't matter. Don't worry about that. Yeah, but it is an estimate, of course, because we're just using some the trapezoidal method, right? That's just an estimate of the area under the curve. That's an estimate of the integral. What else? No? Good. Hi. Okay. Thanks. All right. Well, in that case, let's do some new stuff. Take some notes.
Yeah.
Okay. So first of all, the topic is integral properties. We're just going to talk about some properties of the integral. So the first thing that I want to say, which I think you might have seen in one of the exercises last night, is that integrals, yeah, they give you the area under the curve, although actually it's a little more complicated than that. I think you did an exercise for homework where you computed an integral and it came out to be negative. Does that ring a bell? So what's going on with that? Because like area isn't negative, is it? It's usually a positive quantity. So the first thing that I want to mention is that integrals give what is called the signed area under the curve. All right, they give the signed area under the curve. And what do I mean by that? What I mean is that areas which are below the x-axis are counted as negative. Areas below the x-axis are counted as negative. So some weird stuff can happen as a result of that. Here's an example. I'm going to draw a familiar function. Let's consider sine of x. Okay, what does that look like? It's some kind of wave, right? It actually starts at 0, and then it kind of goes up, and then it comes back down, and then it goes up again. And of course, it repeats in both directions, right? That's just one cycle of it. What is this x value right here? Do you guys remember? How long does it take to complete one full cycle? Like all the way around the unit circle? 2 pi. Is that okay? All right, so that's 2 pi. Now, if I asked you to compute the integral of this function, that is the integral of sine x from 0 to 2 pi, because that integral gives you the signed area, because it treats areas below the x-axis like this one as being negative, what do you think this integral would actually wind up being? 0. It would actually be 0, surprisingly, because these two regions here are equal in magnitude, but opposite in sign. This is positive, that's negative. They exactly cancel each other out. Is that okay? So it's really important to remember that the integral technically gives you not the area, but the signed area. And you need to be careful when you're doing problems to recognize the difference, okay? In a problem, if we ask you for the area, if we just say area, then we mean regular old-fashioned area, not this weird signed area, okay? So if I ask you for the area bounded by this function between 0 and 2 pi, the answer would be, well, some positive number, whatever the real area of those shaded regions would be. Are you with me on that? So just recognize that when we say area, we mean regular area, okay? And the integral doesn't necessarily give you that. It gives you the signed area. So as we'll see, sometimes integrals can kind of mislead you because they give you signed area when maybe you only wanted regular area. Is that okay? That's all I want to say about that. Just something to keep in mind, okay? Questions on this? Okay. So let's talk about algebraic properties. Algebraic properties of the integral. Yeah, I think the display looks pretty good. Can you guys in the back see it? Yeah, is it good? Is it bright enough? Yeah, it's not like the bulb is not strong enough. Like, I shouldn't have to turn off my lights like this to make it visible, but I don't know. Anyway, okay, so just a few algebraic properties. I'm just going to give you 3 of them. So 1. The integral from a to b f of x dx plus the integral from b to c f of x dx is equal to the integral from what to what? A to c. Okay, so that's the first property. Now, why is that true? It's very clear why it's true if you just think geometrically. This integral represents the area under the curve from A to C, or from A to B, right? This guy represents the area under the curve from B to C. If you add those two together, then of course you just get the total area from A to C. Does that make sense? Like if you imagine, A, B, C in a line, area from here to here plus area from here to here is just the total area. That's all that property says. Good? Questions on this one? Okay. Second property, integral from A to A, f of x dx equals, any guesses as to what that might be? I heard it. 0. Yeah, that's 0. Look, again, think geometrically. What does this represent? It's the area under the curve between A and A. That's not really even a 2-dimensional object. That's like a line segment. You know what I mean? Like you think about a curve, if your starting and ending point are the same, then you're basically just talking about a line. Like, well, what's the area of that line? Well, it's 0 because it's infinitely thin. Does that make sense? Okay. So if the upper and lower limits of integration are equal, then you get 0. Good. Last integral property is the following. The integral from b to a f of x dx. Now notice that I've switched the limits of integration. Instead of a to b, it's b to a. That is actually equal to the opposite of the integral from a to b f of x dx. And so what this tells you is that if you switch the limits of integration, that produces a minus sign on the integral. Why this is true? It's kind of true by definition. Like we kind of define this to be true, but an argument for why it should be true is basically these 2 rules. If these 2 rules are true, then it kind of forces this rule to be true. Because look, so here's just a quick proof. Don't copy this down, but here's just a very fast proof. If I take the integral from b to a, and then I add to it the integral from a to b, I can use this first rule here to collapse those 2 integrals into a single integral, right? So if you have 2 integrals where like this guy matches that guy, you can collapse them into a single one, right? That's what this first property says. And that's what I've got here. I've got, this lower matches that upper, or if you like, this one matches this one. Either way, you can view that as integral from, you could either say a to a f of x dx. Maybe I'll say that, a to a f of x dx. Or you could say b to d, and that's 0, okay? So these 2 things added together give you 0, which means that they're opposites, which is exactly what the rule says. So that's kind of a proof of it, right? But the the thing to remember is basically if you switch the limits of integration, you're going to get a minus sign on the outside. Is that okay? We're almost done. I don't have a lot to say today. Take out your graphing calculators. So let's use the calculator to find the area bound by y equals x squared minus 4x plus 3 and the x-axis. Okay. We're going to try to find the area enclosed or bounded by that function. So what should the window be? I would always start with standard. So I'll turn on my calculator. The first thing we should do is just, type that function into the calculator. So I'll go ahead and do that. Y equals x squared minus 4x plus 3. If I hit graph, it looks like my window's already in the standard window, but if yours isn't and your graph doesn't look like that, just hit the zoom button right here and then go down to Z standard, hit enter, and that'll take you back to the standard -10 to +10 viewing window. Okay, so we want to know the area bound by this curve and the x-axis. I'm going to zoom in a little bit to make it more clear what we're talking about. I'm talking about this region here. You guys see that? This region here, that's the region bound by the curve and the x-axis, okay? Now here's the thing. If I ask my calculator for the integral over that region, it's going to give me a negative number because that region is below the x-axis and the integral gives you the signed area. But we are being asked to find the area, the regular old-fashioned area, not the signed area, which means that whatever number we get from the calculator, we're going to have to make it positive. Does that make sense? It's just about recognizing the difference between signed area and area. So I'm going to have to use, second calc. I'm going to go to the integral function under the calc menu, but I have to know the limits of integration. In other words, I have to know these left and right endpoints, right? It certainly looks like it's 1 and 3, but to make sure, I'm going to check because those are clearly just the x-intercepts of this graph. And so I'm just going to quickly confirm what those x-intercepts are. This thing factors as x minus 3 times x minus 1. Okay, yeah, so the x-intercepts are 1 and 3. So that's correct. All right, so I'm going to go to second calc, go down to the integral symbol. Okay, lower limit. I want to emphasize, you do not have to manually move your cursor over. Don't do that. Just enter directly the left limit, which is 1. So just type 1 and then hit enter. Upper limit. Again, don't move your cursor manually. Just enter 3. So hit 3, enter. It fills it out. And it says that the integral is negative 1.333. Camera's not really focusing on my calculator, but so the integral is negative 1.3 blah, 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 1.3 repeating. But of course, we know that the area, not the signed area, is positive 1.3 repeating. Is that okay? Questions on that one? Okay. All right, that's all I got to say.